Dear students, let's proceed with our lectures on the topic of usage of Laplace transformations for determination for solution of transient processes problems and for obtaining transient and forced component. Both we will have do it in not easier maybe, but for branches of the second order it will be just easier to get it with help of Laplace transformation. So let's proceed. I would like to remind you that to get Laplace transformed function, you should take integral from 0 to infinity from the original, from the time function multiplied by e⁻ minus pt, and by dt we will have image by Laplace of this function of time, and p is complex variable p, this operational from operational function c plus j omega. So it differs from just phasor by presentation of IC values with the help of phasors in the form of phasor with the help of complex numbers, but we have here additional item, additional it's this C. It will permit us to apply Laplace transformation, these operational forms, to get solutions of transient processes. So let's proceed, and this operational images by Laplace possess property of linearity, and let's use this property of linearity, okay? And we will use this property to obtain operational image of such function. How can we do it? So operational image of this sphere T, f from P, will be equal to, you see, alpha T. We only recently have got that operational image from function T equal to 1 over P squared 2. So with coefficient alpha, it will be alpha over P squared 2. From this summand, it is here. Then operational image from a unit is 1 over P. It was in previous lecture. It was unit function may be transformed by Laplace as 1 over P. So it's second summand, and at last this summand. We've got that image of function e in the minus alpha t. It's 1 over P plus alpha. So we write it down. As this summand. It's 1 over P plus alpha. And let's rearrange this expression with the common denominator. It will be P power 2 multiplied by P plus alpha. And here we will have this alpha should be multiplied by P plus alpha. It is here. This summand, it should be multiplied by P plus alpha. It is here with minus, yes. And then this item, this summand should be multiplied just by P squared 2. Okay, P power 2, okay. And then let's rearrange it. It will be alpha P for this plus alpha power 2 minus P power 2 minus P alpha and plus P power 2. P power 2 and P power 2 will be cancelled. Yes, alpha P and alpha P will be cancelled also, and we will have only alpha power 2 in numerator. Denominator will be P power 2 multiplied by P plus alpha. This way. So we can write down that operational image of this function, it's equal with these dots. It means that they are not equal, but it's function of time, and it is operational image. It will be equal to this expression. Let's proceed with the most important part of this lecture. It's a differential and integration theorem, and just application of these theorems permit to use this operational method as it was used in phasor method, because this differential and operation and integration theorem will permit, you will see that application of these theorems will permit us to transact from differential equation to just algebraic equation, and to use all known to us methods of solution of different circuits in the form of operational images of the corresponding parameters. So let's find image f from p of function f from t derivative. So let's find operational image of function phi d phi by dt, its designation, and let's do it with usage of integration by parts. So let's write down that operational image of this function, it will be equal to this function multiplied by integral minus pt by dt. And let's use the same approach as previously. Let's determine u by dv. U, it is here, and dv, it is product of dphi by dt multiplied by dt. It is here. Okay, so du from here will be equal to integral minus pt by dt multiplied by derivative from argument. It will be minus p, and v from here will be got by integration of this expression by time, and integral of from dphi by dt by time equal just to phi from t. Okay, so let's write down that this u multiplied by dv will be equal to u multiplied by v, it's e in minus pt degree, multiplied by f from t. F, you see, is just function which derivative, image of which derivative we would like to get. So it will be this product u multiplied by v minus, it will be u by dv, it will be v by du here, by the rule of taking derivative by parts. So it will be minus p multiplied by integral minus pt, yes, multiply du multiplied by f from t, okay, by dt. This dt, it is here. So let's consider this. Let's consider this summand. When we substitute here infinity, this coefficient, this part will be equal, will tend to 0. So it will be 0 for the upper limit, and for the lower limit we will have e in 0 degree, it's 1, and phi from t at t equal to 0, it will be phi from 0, and with minus because it's lower limit, so minus phi from 0 from this part, and here it will be you see, phi from t multiplied by e in the minus pt, it's just designation of phi from p. It's image by Laplace of this function phi from t. So we can write down that it will be equal to this part. It will be equal, integral from this part will be equal to f from p, and it should be multiplied by minus, and minus will give us plus multiplied by this coefficient p. So we've got such an expression. So we can write down that image by Laplace of derivative of some function by time equal to p multiplied by image by Laplace of this function, yes, which derivative we determine here, minus phi from 0. So differentiation operation corresponds to multiplication of image by Laplace of the original function multiplied by p, and it should be taken into account initial conditions will be minus phi from 0. This function from at 0 moment. It's differentiation theorem. Please remember it by heart, and you should understand how it. So operation of integration of differentiation may be replaced in at usage of Laplace transformation by multiplication by this uh, by this p variable of Laplace transformation. And let's consider integration theorem. Integration theorem tells us that operation of integration may be replaced by just division of operation of Laplace image of function divided by p, by Laplace variable p. For this, to prove this, let's find out image of finite integral from function phi from t by dt in the limits from 0 to t. And let's use here also integration by paths. So image by Laplace phi from p of this function integral from phi from t by dt. To get it, we should multiply this function by integer minus pt and multiply it by dt, as it was in definition of obtaining Laplace images. So let's take it by parts, and let's designate here is integral u multiply u by dv. Here let's designate u as this expression phi integral from phi from t by dt. It will be, this will be u. Du and dv here, it will be easily minus pt multiplied by dt. Therefore, du will be equal, when we take derivative from this integral, it will be just under integrand expression, yes? And if we have such dv, from here we can determine v by integration of both sides of this expression. It will be v equal to integral from exponential function is just exponential function, and it should be divided by minus 1 over p, where p minus 1 minus p, its coefficient of the exponential function. So it will, such an integral will be equal to u multiplied by v. It is here u, here multiplied by this p. It is here in limits from 0 to infinity, in these limits, minus, it will be u multiplied by dv, and here it will be v multiplied by du. This minus will give us plus, it will be 1 over p. This e in the degree minus pt, this is 1 over p, yes, and it should be multiplied by du. It will be phi from t by dt, okay? And this expression, it is just image by Laplace of function phi from t. It was in the very beginning, you see, it's definition of Laplace transformation. So it will be here, it will be phi from p over p, this expression, and this expression equal to 0. Why? Let's see. When we substitute here infinity, this expression will give us 0, because integration oh sorry, this part will give us 0 because e in minus infinity equal to 0. Okay, so 0 multiplied by function, it will be 0. Then let's substitute lower limit. It will be integral from 0 to 0 phi from t by dt, and such an integral will be equal just to 0. So we have in both, at substitution of both limits, we will have here 0, therefore we will, this summand will vanish and we will have only this summand, and we can say that integration operation corresponds to division of original's image by p. So integral from phi from t by dt equal to in terms of transaction from function of time to Laplace image, and it may be presented in such a form, and therefore we can transact from differential integration equation to just algebraic equation. Let's proceed in the next lecture. Bye bye for now.